given y. That's the growth rate of wealth if you had side information. And with no side information, we've already calculated W star of x is equal to summation P of x log O of x minus H of x. That's when B equals P. All right, so we have those two. And so delta W increase in W, that's delta W, is equal to the old exponent subtracted from the new exponent. The summation P log O cancels out in the sum, and we're left with H of x minus H of x given y equals the mutual information. So the two things we've gotten from the calculation are, if you have side information, bet according to in proportion to the conditional probability. And number two, your increase in the exponent will be the mutual information. So here's an unexpected occurrence of mutual information in a concrete setting that tells you how fast your money will go to infinity. And it's the optimal use of the side information. Let me tell you that gambling is a better way to elicit a good forecast than just asking for what's going to happen next. Let's look at the value of side information to a weather forecaster. He says the probability of rain tomorrow is 70%. This is without side information. Then a storm is coming down from the Sierras. And so he says, given that side information, the probability is now 80%. The gambler switches a 70% bet to an 80% bet. The weather forecaster just says it's likely to rain tomorrow in each case. In other words, there's a discreteness to what we're asking of a weather forecaster. If we don't ask him for the odds, we just say, what do you think is going to happen tomorrow? The prediction of both forecasters, with and without the side information, will be the same. That's why I think gambling is a natural way to elicit the true probability. Okay, now there's some nice applications of this. Applications. Here's one. Let side information be the past. So x sub n is a stochastic process. It's the outcome of the nth horse race as n runs from, say, 1 to whatever, the future, 1 to infinity. Now you ask, And let's not assume that the x's are independent, identically distributed. In fact, they aren't. You see the past history of the horses. So in any case, you have a p of x1 through xn. This is the true probability distribution on who wins each race. The x's take the integer values 1 through m. And we look at B star. What should you do in the nth race? Given the side information x sub n minus 1. So this takes the place of y in our previous calculation. It's just the past outcomes. But we know that that should be equal to p of xn, given x sub n minus 1. That is the true conditional probability of xn, given the past outcomes. Note that B star of x1 through xn is the product of B star xi given xi minus 1 which is equal to the product of the p of xi given xi minus 1 is x1 through xn. You say, wait a minute. Here I'm betting sequentially on the next horse race given the past. And here I'm combining them all to see how much total money I have bet on the specific set of outcomes, say horse 3, horse 2, horse 3, horse 7, etc., etc. And it turns out this behaves exactly like a probability mass function. So, you can think of betting as sequential or as a batch. Sequentially, you bet on each horse race, given the past, or as a batch, you bet on the outcome of all n horse races. There are m to the n possibilities, and the proportional wealth you put on one of those possibilities is precisely this. These are non-negative and sum to 1. So they are equivalent. So betting is just like prediction. Look, if I asked the weather forecaster probability of rain tomorrow, he'd give me this. And if I bet, I'll do the same with the same information. I'll bet in proportion to the conditional probability. Okay, but now let's look at what this means. This means 1 over n, expected value of log of S star of x super n. That is the amount of wealth I have at time n, maximized over all betting schemes. Equals the product of m. Let's say these are fair odds, uniform fair odds. M times B of xi given x super I minus 1 from I equals 1 to n. But this then is m to the n times the amount B. I'll put B star here because I want it to be the optimal one. B of x super n by this previous computation, which is sorry, there's a log here. 1 over n log of this product. 1 over n log of this. And this is P of x super n. And so we see this, the log m to the n is n log m divided by n, that's log m. So we get log m minus I have an expected value, sorry, equals expected value of all this. Expected value of all this. And this is minus summation P of xn log P of xn. And it's plus. All right, so what do we have? My expected growth rate of wealth, the term in the exponent, is this. But notice this is n1 over n times this. Huh. Okay, let me collect. Ta-da. This all works out just like a puzzle. It all fits together. And the generalizations then become natural, but another time for the generalization. But look at what this is. 1 over n, expected value of log of s n star of this random process, xn, not IID, just whatever, a stochastic process horse race, is equal to log m, and this is summation p log p over sequences xn. This is minus h of x super n over n. Look at this. This is the entropy of the batch of horse races from n horse races divided by n, and we know that for any stationary process this has a limit, and this converges to log m minus the entropy rate of the horse race. For xi stationary stochastic process. Stochastic process. So the rate at which you can make money is a constant minus the entropy rate. So we have now generalized a single one-shot gamble, or IID gambles, to gambles which are dependent. So the expected log, the growth rate, this is sort of W star, indexed by n, it converges to log m minus n. And now again we have h plus w equals log m, where this is w infinity, that is the limit of w sub n star as n tends to infinity, and this is the entropy rate, which, if you will, is the limit of this as n goes to infinity. So, again, anything you can save, every bit you can save in the entropy rate, that is